In this video, I will discuss some collision problems from previous year's question papers of NEET. This is the first question. An object flying in air with velocity 20 I cap plus 25 j cap minus 12 k cap suddenly breaks in two pieces whose masses are in the ratio 1:5. The smaller mass flies off with a velocity 100 I cap plus 35 j cap plus 8 k cap. The velocity of larger piece will be. You can pause and attempt this question. Here is the solution. So after breaking up, the masses are in the ratio 1:5. So if we call the smaller mass as m, the bigger piece will be 5m, and the initial mass, which is the sum of these two pieces, will be 6m. So the initial velocity of the mass is 20 I cap plus 25 j cap minus 12 k cap, and the velocity of the smaller mass after breaking up is 135.8. So we have to find the velocity of 5m after breakup. So this can be solved by using conservation of momentum. So the initial momentum of the system is the initial mass 6m into the initial velocity u, and the final momentum of the system is m v1 plus 5m v2. So using the values of u as 20, 25 and minus 12 and v1 as 135 and 8, we can get v2. The simple calculation, so this will give as v2 as 4 I cap 23 j cap minus 16 k cap. So correct option is option E. This is the next question. A particle of mass 5m at rest suddenly breaks on its own into three fragments. Two fragments of mass m each move along mutually perpendicular direction with each speed v. The energy released during the process is. You can pause and attempt this question. So initially the mass is 5m, and after breaking up, two of the masses are moving perpendicular to each other with velocity v, and the remaining mass, which is 3m, will move in this direction so that the momentum of the system is conserved. Initially the momentum is 0 because the initial mass is at rest. So we have to find the energy of release. So we can apply conservation of momentum. Initial momentum is 0, so final momentum is 3m into v1. Actually velocity is a vector quantity, so we have to take components. So writing the momentum conservation in the x direction, we get 3m into v1x plus m into v equal to 0. So from this I get v1x as minus v by 3. X-axis towards right and y-axis upwards. And momentum conversion in the y direction will give exactly same set of equations. So v1y is minus v by 3. So the energy of the final system is half m v square. Two of them are there, and then half 3m into its velocity square v1 square, that is v1x square plus v1y square. So it is v square by 9 into 2. So simplifying, we get 4 by 3 mv square. Correct option is option D. This is the next question. A body of mass 4m moving with speed u collides with another body b of mass 2m at rest. The collision is head-on and elastic in nature. After collision, the fraction of energy lost by colliding body E is. You can pause and attempt this question. So initially the mass E, which is 4m, is moving with velocity u, and the body B of mass 2m is at rest. So after collision, let the velocities be v1 and v2. So to find the energy of E that is being lost, so we can apply conservation of momentum. It's a 1D problem. So initial momentum is 4m into u, and final momentum is 4m v1 plus 2m v2, and coefficient of restitution is minus final relative velocity divided by initial relative velocity. So final relative velocity is v1 minus v2 divided by u minus 0. So, and it's a perfectly elastic collision. So E is 1. So from this, I get U as V2 minus V1. So we have two equations in two unknowns. The unknowns are V1 and V2. So we have to find V1. So V2 I can write as U plus V1. So from the first equation, I get 2U equal to 2V1 plus U plus V1. I can cancel 2M in this first equation on both left and right side. So from this, I get U as 3V1, or V1 is U by 3. So energy loss of A is final energy minus initial energy. So half mass is 4m. So final velocity square, or initial velocity square, is U square minus final velocity square is U square by 9. So 8 by 9 U square into half into 4m. So correct option is option E. So the fraction is 8 by 9. This is the next question. A block having mass m collides with stationary block having mass 4m. The lighter block comes to rest after collision. When the initial velocity of the lighter block is v, the value of coefficient of restitution will be. You can pause and attempt this question. So the block m, which has got initial velocity u, and the block 4m, which has got initial velocity 0, that is at rest. And after collision, this thing comes to rest, and we have to find the velocity of the second block after collision. So writing conservation of momentum, initial momentum is m into u, and the final momentum of the system is 4m into v2. So from this we get v2 as u by 4. Coefficient of restriction is defined as final relative velocity divided by initial relative velocity with a negative sign. So final relative velocity is v2 minus 0. Initial relative velocity is 0 minus u. So from this we get the coefficient of restitution as 1 by 4. Correct option is option B, which is 0.25. This is the next question. Two identical balls A and B having velocities 0.5 meter per second and minus 0.3 meter per second respectively collide elastically in one dimension. The velocities of B and A after collision respectively will be. You can pause and attempt this question. So there are two identical masses m and m. One is got velocity 0.5 meter per second, other one is minus 0.3, and it's an elastic collision. So E is 1. So you have to find the final velocity of both 1 and 2. So using conservation of momentum, initial momentum is of the system is m into 0.5 plus m into minus 0.3 equal to m into v1 plus v2, and coefficient of restitution is minus final relative velocity divided by initial relative velocity. So that is minus v1 by v2 divided by 0.5 minus 0.3. So from this we get v2 minus v1 as 0.8. So you have two equations in two unknowns, that is v1 and v2. So adding 1 and 2 we get v2 as 0.5 and v1 as minus 0.3. So correct option B. Here we can also use a standard result. If you have two identical masses, when they collide elastically, after collision the velocities will get interchanged. So these are two identical masses with velocities 0.5 and minus 0.3, and after a perfectly elastic collision, the velocity of the first one will go to the second and velocity of the second will go to the first. That is the same thing we got by calculation. This is the next question. On a frictionless surface, a block of mass m moving at a speed v collides elastically with another block of same mass, capital M, which is initially at rest. After collision, the first block moves at an angle theta to its initial direction and has speed v by 3. The second block speed after collision is. You can pause and run this question. So initially, the first mass m is moving with velocity v, and the second mass m is at rest. And after collision, one of the mass moves with, actually the second one moves with velocity v by 3 at an angle theta. So you have to find the velocity of the other one, its value. So the first block moves at an angle theta after collision. So this is the first block. and this is the second block. So writing conservation of momentum in the x direction is a 2D problem. We get m into v, that's the initial momentum, taking the x direction as towards right, equal to m into v by 3 cos theta plus m into v2x. And writing conservation of energy is a perfect elastic solution, so there is no energy loss. So initial energy of the system is half m v square. That should be equal to the final total energy, that's half m v square by 9 plus v2 square. So from this we can get v2 square as 8 by 9 v square, and so v2 is 2 root 2 by 3. So we don't have to use this momentum conservation equation. We'll get the answer just by using the energy conservation equation. The correct option is option E.